Hi, I am Nicole Daurizio and I'm here to present this project entitled No Face Touch, an open project to limit the COVID-19 outbreak. This project is funded by the IEEE Robotics and Automation Society, special interest group on humanitarian technology, and it has been motivated by the alarming morbidity of COVID-19, which has drawn the attention on the social role of hygiene rules, in particular on the importance of limiting face touch occurrences. The face touch action is very often performed involuntarily and occurs with little awareness, several times per hour. For being of help during the pandemic, our idea was to develop a ready and easy to use and a large-scale deployable solution for estimating hand proximity to face and notifying the user with an haptic signal whenever a face touch movement is performed. The core of the project is an application that runs on smartwatches, the No Face Touch app, which can be adapted for fitness bands and do-it-yourself electronic bracelets. Conceptually, the No Face Touch system has been designed to have an immediate reduction of face touch occurrences, and thus to decrease the probability to get infections from the environment. In addition, the aim is to have a mid-long-term enhancement of the subject proprioceptive awareness, potentially making the device itself no more necessary. As we all know, the most common ways of spreading the COVID-19 virus are two. The first is the airborne transmission, which is the most common way, but also controllable by wearing masks and respecting social distance. The second is the self-inoculation, that is the transfer of contaminated material from hands to other body sites. The second way is less frequent, but more difficult to prevent due to the common habit of touching the face. Our project wants to tackle the self-inoculation issue. Indeed, our solution is thought to minimize the mental effort required to keep hands away from the face, catching also involuntary contact occurrences that will take place without the subject noticing. Our project wants to tackle the self-inoculation issue. Indeed, our solution is thought to minimize the mental effort required to keep hands away from the face, catching also involuntary contact occurrences that will take place without the subject noticing. Among the policies adopted in response to COVID-19, individual protective behaviors have a profound effect on the reduction of the pandemic spread. Protective behaviors can be classified into three groups: preventive, avoidant, and management of disease. No Face Touch project intervenes in the context of preventive behaviors by detecting users' attempts to touch their face and stopping the action. As regards the coronavirus, if the virus is transferred to eyes, nose, or mouth, it can enter the body and infect the subject. Therefore, avoiding face touches is a crucial novel habit that has to be acquired. Face touch occurrences are often involuntary and occur with little awareness. This aspect is further supported by a behavior observation study where 26 subjects were observed and videotaped to monitor the occurrences of face touch. During the study, the frequency of hand-to-face contacts with the mucosal or non-mucosal areas was tallied and analyzed. On average, subjects touched their face 23 times per hour. Of all face touches, it has been estimated that the contact involves a mucous membrane about half of the times. The two main elements of No Face Touch are a smartwatch worn by the user and the No Face Touch application running on the smartwatch or on the companion smartphone. Measurements from magnetometer, accelerometer, and gyroscope are used to estimate the hand proximity to the face. According to the sensor availability in different devices, as first step we developed two algorithms. The first takes advantage of data coming from accelerometer, gyroscope, and magnetometer sensors, while in the second case only acceleration and gyroscope measurements are used. Indeed, this second method accounts for the fact that many smartwatches do not feature a magnetometer. Although less robust, in our regards, it was worth proposing an alternative approach to provide support to the widest possible amount of people. As a preparatory phase, we identified a range of admissible wrist orientations for face touch events, with the aim of establishing discriminatory conditions for the face touch detection. Considering that not all wrist orientations are compatible with natural touches of the face, we selected a narrow subset of all the possible wrist orientations on the basis of anatomical constraints and experimental results. In the magnetometer version, the user is asked to wear close to the face a wearable accessory with some magnets attached in order to generate a detectable magnetic field. Such arrangement is adequate to detect the smartwatch proximity around the necklace as a result of the significant magnetic field generated by the magnets. Thanks to the calibration procedure, a different number of magnets with different technical specifications can be employed, allowing each user to build his own wearable accessory with great flexibility. Thus, the discrimination of hand movements based on wrist orientation is refined thanks to a virtual magnetic barrier generated by the word magnets. First, the algorithm performs hand gesture recognition through the smartwatch inertial measurement unit. Then, if the current wrist orientation is considered potentially compatible with a face touch, the magnetic field measurements are analyzed to detect deviations from the baseline. If the smartwatch is considered too close to the face, a vibratory alert is triggered to acknowledge the user to stop the current hand movement. As previously said, the accelerometer version was developed to extend the app usage to older or simpler devices, which do not embed a magnetometer. The arm pose is estimated by processing measurements from the smartwatch accelerometer and gyroscope. By taking advantage of biomechanical constraints of the human body, we can predict if the current combination of wrist orientation and acceleration profile conducts to a face touch. If the app detects hand raising motion and the wrist orientation is within the face touch compatible range, then the user receives an alert. Clearly, there are many gestures that correspond to the subset of movements identified by the conditions defined. To assess the no-face touch functioning, we conducted an experimental evaluation on 10 participants. They were tasked to perform two trials. First, attempt to touch their face 30 times, and second, simulate 30 common gestures of activity of daily living. Subjects were asked to wear the smartwatch and perform twice both trials, once with the magnetometer version and once with the accelerometer one. As it can be seen in the graphs, the algorithm relying also on the magnetometer sensor is more robust and more accurate than the other. In addition, it is worth pointing out that the higher percentage of correct detections scored by the second version is biased by the large amount of false positives. In fact, this algorithm is prone to exceed in alerting a user, regardless of the specific gesture, hence affecting the effectiveness of our idea. Once the two versions were compared, we performed an experimental campaign to evaluate the effectiveness of no-face touch with the magnetometer version. 10 subjects were asked to wear the smartwatch for 6 days, 8 hours per day. All the events in which the users crossed the virtual magnetic barrier and the related duration were recorded. Each day, the vibratory alert was active half of the time, meaning that in the remaining 4 hours, the face touch events were detected but not notified. The first histogram shows that unsafe gestures were observed more often when no vibration was provided to the user than in case of vibrotactile notification. The second histogram reports the number of face touches per hour, that was smaller when subjects used the system with the haptic feedback enabled. From the third histogram, it is evident that the duration of face touches was significantly reduced, from a median value of about 5 seconds when participants were not notified to 2 seconds if the smartwatch vibration was enabled. While the reduction of face touches due to the vibration could be expected, the most interesting result is the fact that also the number of touch attempts is reduced, as shown in the first histogram. This may suggest a training effect that could be exploited to prevent unhealthy habits, but it has to be further assessed in future works. To tackle the lack of accuracy of the accelerometer version of No Face Touch, we are currently developing a machine learning-based gesture recognition exploiting temporal sequence analysis of accelerometer data. In particular, this new version implements a recurrent neural network which achieves good generalization capabilities to data coming from different users. At the same time, this network is potentially tunable according to some specific user behavioral needs. With this new version, any device embedding an accelerometer meets the No Face Touch requirements, since accelerations allow a simple physical description of the gestures, without additional features. To evaluate the neural network performance, we compare this new version with the previously developed approach that exploits only inertial measurements. In this step, data acquisition involved 5 subjects. 12 recordings have been acquired with an overall duration of about 75 minutes. During experiments, participants were asked to freely perform gestures related to activities of daily life. The same recordings were used to test both algorithms. Results reported in the graphs show that acceleration data can be successfully exploited as input to the No Face Touch recurrent neural network, achieving a false detection rate of about 2.9% and the highest score for true detections, which is higher than 99%. As it can be easily envisaged, developing technologies for gesture detection with low false alarm rate is a requirement for effective and comfortable use of technologies. In this video, there is a demonstrative trial with no face touch featuring the recurrent neural network approach. As soon as a face touch is detected by the network, the smartwatch vibrates, alerting the user. In the video, you can hear the vibration burst and see the smartwatch screen becoming red. The traffic light mirrors the smartwatch screen color. Since No Face Touch is an open project, all the software mentioned was developed by the authors and is freely available at the No Face Touch GitHub public repository, released under the new GPL software license. Alongside the head models, we share the trained neural network model and the code related to the 3 algorithms presented, believing in the power of cooperation and new philosophy. The opportunity of developing do-it-yourself devices makes this solution suitable for everyone and exploitable also in underdeveloped areas, in the Rust side spirit. Thank you for the attention.